Hey guys, welcome. In the last lecture, we discussed about setup and hold time definitions. So let's revise them quickly. What do you mean by setup time? It is nothing but the minimum time before the clock edge, for which the input should be stable. And what do you mean by hold time? It is also the same, the minimum time, but after the clock edge, for which the input should be stable. Right? So if you take this clock, this is the clock for flip flop 1 and this is the clock edge. So the input should not change for the minimum time before this clock edge. So let us say this has TSU and it should also not change after this clock edge for some time. So this is called as TH. So at the end, the input should not change in this duration. That is TSU plus TH. Otherwise, our output will go into metastable state. And the minimum time is called as setup time and hold time. So this is clear, right? And what about this combinational circuit? We discussed in the first lecture. This is having two delays, critical path delay and contamination delay, where critical path delay is the maximum delay and contamination delay is the minimum delay. The minimum time required to see the change in the output is called as contamination delay, and the time required to make the output stable, the time required for the output to be stable is called as critical path delay, otherwise maximum delay. So these three things you should remember from our previous lecture. Let me erase this. Now, till now we have discussed about a single flip-flop. Now let us see what will happen if we connect two flip-flops like this. So this is clock for the flip-flop 1 and this is the clock for the flip-flop 2. In this circuit, both clocks are same, but if I introduce some delay, they will change. So that's the reason, to maintain some clarity, I have differentiated them. Next, this is the input to flip-flop 1 and D2 is the input to flip-flop 2, right? This is for flip-flop 1 and D2 is for flip-flop 2, that is input. So whenever we are checking the setup time, we should check the input, right? Let us say this is the clock for FF2. So before the clock edge, the input D2 should be stable for some time. Now let us talk only about setup time. About hold time we will discuss in next lecture. Okay. So before this clock, our input D2 should be stable and the minimum stable time is called the setup time. If you take the flip-flop 1, there is the clock. The minimum time before this clock edge, the input should be stable. That is called as setup time for flip-flop 1, right? So as of now, this input is coming from some external source. We are not worried about it. We will be checking the setup time violation for flip-flop 2. So the flip-flop 1 is launching this input and flip-flop 2 is capturing it. So that's the reason we'll call this as launch flip-flop, and we'll call this as capture flip-flop, right? Great. Now let's see the timing waveform. So these are two clocks and this is the input. So at the clock edge, the flip-flop 1 will clock this input and it will propagate to the output, right? So at this clock edge, the flip-flop 1 is clocking A, and after some clock to Q delay, Q1 is getting this. So this transition is clear, right? Next, what is happening from here to here? D2 will be getting Q1 after this combinational circuit delay. So let me write here D2 will get Q1 after combinational circuit delay. If there is no combinational circuit, D2 is directly equal to Q1. Since there is CC, D2 will be getting Q1 after this delay. So if you see here, this is Q1, and after the combinational circuit delay, we are having D2 here. Here we are having A. After some delay, we are having A here. So if you see from this clock cycle, first what happened? The input is clocked. After clock to Q delay, you are getting Q1. After combinational circuit delay, you are having D2, right? And we can also see at this transition. At this transition, B is being clocked. After clock to Q delay, you are getting Q1 here. After combinational circuit delay, you are getting D2. So clock to Q delay plus combinational circuit delay. So these transitions are clear, right? Next. Now we have D2. In the next clock edge, this flip-flop 2 is ready to clock D2, right? So here it is ready to clock D2. So what is the definition of setup time? The minimum time for which the input should be stable before the clock edge. So in this scenario, what will be the setup time definition? The minimum time for which input D2 should be stable. Before clock edge. And let us say this is the setup time, TSU. So if I see here, at this clock edge, the input T2 is stable for time T, let us say. So T is greater than setup time, right? This is TSU and this is T. So in this case, T is greater than TSU. There is no violation. Okay. Now let us say the combinational circuit delay is more. What I am telling is this is my D2. The delay is higher. So there is clock to Q delay, and combinational circuit delay. Now if you observe, this is the clock edge and this is the setup time. but the input is not stable in this range. Input is only stable till here, right? In the whole range, it is not stable. So T is less than TSU. This is TSU, but it is only stable in the interval T. This T is less than TSU. So in this case, there is a setup time violation. Great. Now you understood, right? How these delays affect the setup time. Now let us try to write some formal equations for this. So generally what we checked, at this clock edge, we are launching this data, and at this clock edge, we are capturing the data. So after launching the data, there will be clock to queue delay, combination circuit delay, and it should also have provision for the setup time. So from this distance from this clock edge to this clock edge should have provision for clock to queue delay, combination circuit delay, and TSU. This will be the worst case condition. If the distance is more than this sum, then well, right? But if the distance is less, then there is a setup time violation. I think now you have a clarity. Let me write these equations. The distance between here and here is nothing but T clock, right? So T clock should be greater than or equal to. Here we are launching. First we will be having clock to Q delay. So T clock to Q delay plus next we will be having combination circuit delay. T combination circuit delay plus next it should also follow the setup time. Let us say this is the delay, and in the worst case condition, let us say it is just satisfying the setup time. In that condition, this will be the setup time, right? Because this is the clock edge, this should be the setup time. So this clock to Q delay plus combination circuit delay plus setup time should be equal to this T clock in the worst case condition plus T setup time. So this equation is clear, right? If the distance between these two edges is more, then it is good, right? There will be less chances for violation. But if the distance between these two edges is less, then there are chances for violation. Next, in some cases, the combination circuit delay is mentioned as maximum and minimum. Maximum is nothing but critical path delay, minimum is nothing but contamination delay. Now, what should you take in this case? Always remember we should consider worst case condition. If CC is minimum, then at this edge, input will be clocked, is clock to Q delay. If CC is minimum, the input will change before only, right? It will change here itself. So there are less chances for setup time violation. But if CC is maximum, after this, if CC is maximum, the input may change here. There are high chances for setup time violation. So the worst case condition is combinational circuit delay is maximum. This is the worst case condition. So if two delays are given, I need to take CC maximum, or let me write critical path delay TCP. So this is the formula for the T clock. And from this T clock, we can also get our maximum frequency, which is 1 by T clock. The maximum frequency that the circuit can operate while not violating the setup condition. I mean setup violation. So if this is clear, now I will change the circuit a little. I will introduce a small delay here. This delay is called as skew. Now what will happen? Due to this delay, the clock 2 is shifted a little bit with respect to clock 1. And let me take this delay as delta. Now this clock 2 is shifted by delta. This is delta. Now you should be able to write the equations. At this clock edge, we are clocking this input, and there will be clock to Q delay, and there will be combinational circuit delay. Let us say we are clocking this input, there will be clock to Q delay, there will be combinational circuit delay. But if you observe here, we got more time. Previously, we are calculating the setup time from here, but now we also have an additional time delta due to this shifting, right? So indirectly, the distance between these two clock edges got increased. That makes us less prone for the setup time violation. So this is a good thing. You're able to see it, right? Now what will be the worst case condition? This clock to Q delay plus combinational circuit delay. Now we should take from here. This should be TSU. This is the worst case condition. And this whole thing should be equal to T clock period plus delta. You're getting it, right? The distance between two edges got increased. So now this formula gets changed to, and it's okay, sir. T clock plus delta. Yeah, correct. Now in some questions, delta max will be mentioned and delta min will be mentioned. So what to take? Always remember we need to check for the worst case condition. So if delta is maximum, the distance between these two clock edges will be maximum, right? And if delta is minimum, the distance between these two clock edges will reduce when compared to this case. So delta minimum will be the worst case condition. So this delta will be minimum. Should always check this distance. If it is maximum, then there is less chance for setup time violation. If it is minimum, there is more chance for setup time violation. I mean in the worst case condition. So this delta should be minimum. Next. Now let me introduce this Q in clock 1 instead of clock 2. So generally with respect to flip-flop 2, this is called as data path and this is called as clock path. Till now we introduced the delay in the clock path. Now let me introduce the delay in the data path. You will be perfect in these concepts only when you practice these timing waveforms. Now I need precision eraser again. So just a sec. introduce the delay here, skew, and let that be delta. Now this clock waveforms will also change. Instead of clock 2, now clock 1 will be delayed. Like this. Now this duration is delta. So how will our formula change? At this clock edge, the input is clocked, and after T clock to Q delay, you will get Q1, and after CC delay, you will be having D2. And if you observe here, the distance between the two clock edges got reduced, right? So what is the distance? T clock minus delta. In the space itself, it should accommodate clock to Q delay and combination circuit delay and T setup time from here to here. You see, right? Clock to Q delay, combination circuit delay, and T setup time in the less interval. So this interval is T clock minus delta. So now T clock minus delta should be greater than or equal to T clock to Q delay plus T critical path delay plus T setup time. Now, in the question, what if we mention delta maximum and delta minimum? You should take the worst case condition, and that condition is distance between these two clock edges is minimum. So if delta is minimum, the distance will increase. The clock may be from here itself. Sorry, the clock may rise from here itself. So distance got increased. Now if this delta is maximum, this will be my clock. The distance got reduced. So the worst case condition is less distance. That's the reason in this case delta will be maximum. So generally, whenever there is a skew in the data path, we should take the maximum delay. And whenever there is a skew in the clock path, we should take the minimum delay for the worst case condition or to calculate the maximum frequency. And the concept I just explained here, if you want it, you can draw your own timing diagrams and check yourself. Then you will get more hold on the concept. Now, what if I introduce delay both in data path and in the clock path? Let us say this is delta 1 maximum, delta 1 minimum, and this is delta 2 maximum and delta 1 minimum. So first, let us see this. You can apply superposition. You can neglect this and you can first do this. And after you can neglect this and you can do this. I kind of like that. So due to delay in clock path, just a sec. Yeah. Due to delay in the clock path, the clock 2 will get shifted. Due to this, our distance will increase. That's the reason we will write T clock plus delta. And the worst case condition is delta minimum. Because if delta is maximum, the distance will be more. If delta is minimum, the distance will be less. So we need to write T clock plus delta minimum if the delay is in the clock path. So T clock plus delta minimum, the delta to minimum. And if delay is there in the data path, the clock 1 will be shifted. Due to this, the distance will decrease, and that will be T clock minus delta. And the worst case condition is if delta is minimum, the distance will be more. And if delta is maximum, and if delta is maximum, the distance will still reduce. So the worst case is T clock minus delta maximum. So minus delta 1 maximum. So this is the overall equation. Now, if you want to find the maximum clock frequency, if max equal to, this will be 1 by T clock minimum. And T clock minimum is nothing but you need to derive from this formula. T clock plus delta 2 minus delta 1 should be equal to T clock to Q delay plus T critical path delay plus T setup time. So from this, you can derive T clock minimum. And of course, delta 2 should be minimum and delta 1 should be maximum. Remember these things. Clock path should be minimum and data path should be maximum. And if you forgot at any time, you can easily derive these things from the timing waveform, depending upon the distance between these two clock edges. That's it, guys. This is about setup time violation. In the next lecture, we will discuss about hold time violation. Till then, enjoy your day. See you.